We are given a string num representing a non-negative integer and an integer k, and we should return the smallest possible integer after removing k digits from num. This is not necessarily an easy problem, but we can make it easier by starting with simple examples. Such an easy example can be one where k is equal to 1. So let's say our number is 7772 and k equals 1. I chose this number purposely because it only has two distinct digits. So we can either remove 1 7, it doesn't really matter which one of them, or we can remove the 2. If we remove one of the 7s, we will get the number 772. If we remove the 2, we will get the number 777. Between these two, of course, the first one is the smallest, so it's better to remove a 7 than to remove the 2. One example is not enough. Let's take a second one, where the number is 2777 and also k equals 1. We can remove the 2, and we will get the number 777, or we can remove one of the 7s, and we will get the number 277. Between these two, the second one is the smallest, so it's better to remove the 7. We might notice a pattern here. The first observation might be that removing greater digits is better. Does this make sense? Of course it does. Removing greater digits means keeping smaller digits in our number, which of course will give us a smaller number. But this is not enough. Let's take a third example. Let's say the equal digits are not contiguous anymore, and we have the number 7727 and k equals 1. Now we have three possible scenarios. We can remove one of the first two 7s and we will get the number 727, or we can remove the 2 and we will get the number 777, or we can remove the last 7 and we will get the number 772. The smallest one is the first one, which means that removing one of the first two 7s is actually better than removing the 2 or removing the last 7. This is interesting. So the observation that removing greater digits is better still holds true, but we can also notice that removing one of the first two 7s is actually better than removing the last one. So we might make another observation here, that also removing digits from the left is better. And now we have a better clue about how to solve this question. But let's take a final example. Let's say the number is 54321 and k equals 1. We can either remove 5 and we will get 4321, or we can remove 4 and we will get 5321, or we can remove 3 and we get 5421, we can remove 2 and we get 5431, or we can remove 1 and we get 5432. Obviously, the first number is the smallest, so it's best to remove the 5. And here comes the interesting part. By only looking at the first two digits, we can already know that removing 5 is optimal, no matter what the other digits are. Because if we remove the 5, in the worst case scenario, our number will start with a 4, so it's gonna be 4000 and something. But if we keep the 5, we are guaranteed that our number starts with a 5, so it will be 5000 something, which is obviously greater than the first number. This is a great hint that we can possibly be greedy with our solution, meaning that by only looking at the first two digits, we will know what is the best decision to make, even though we haven't gone through the rest of the digits and we don't know their values. Let's see if this also holds true for k equals 2. We have to remove two digits, which means that we will be left with 3 digits, and if we choose not to remove the 5, we are going to be left with a number like 500 and something. But if we remove the 5, in the worst case scenario, our first digit will be 4. And I'm saying worst case scenario because let's suppose we don't know what the other digits are. So in the worst case, we will still start our number with a 4. Our number will be at most 400 and something, which is less than 500 and something. So yes, it's still best to remove the 5 even if k equals 2. Does this hold true for k equals 3? We are going to be left with two digits, and if we choose not to remove the 5, our number will be 50 something. But if we remove the 5, in the worst case scenario, our number will be 40 something, so it's still better. So the solution to this problem might be a greedy one, and we might need to traverse the digits of num from left to right, and also keep our current solution. For each current digit, if this digit is less than the last digit from the solution, then it might be best to remove that digit from solution and add this current digit instead. Let's finish completing this example to see if it makes sense. The solution is initially empty and we start traversing the digits of num. The first one is 5. Because solution is empty, we have nothing to remove, so we will just insert 5. Then, the next digit is 4, which is less than 5. So it's best to remove the 5 and keep the 4 instead in our solution. And we are left with 2 removals. The next digit is 3, which is less than 4. So it might be best to actually start our solution with this 3. So to remove the 4 and keep the 3 instead. And we will be left with 1 removal. Next digit is 2, which is less than 3. So it's best to remove the 3 and keep the 2 instead. And we are left with 0 removals. Next digit is 1, which is less than 2. So yeah, it would be best to remove the 2 and keep the 1 instead, but we don't have any removals anymore. So we can't remove the 2, we will just push 1 to our solution instead. And the solution is 21, which is indeed the best one. And now it's time to look at the original problem example and see how our algorithm works on it. Solution is initially empty and we start iterating through the characters. The first is 1. Obviously, we have nothing to remove from the solution, so we will just append 1. The next character is 4. Let's compare it to the element on top of the solution, which is 1. 4 is greater than 1, so of course it doesn't make sense to remove 1 and use 4 instead. This will give us a greater number. So we will just append 4 to solution. The next character is 3, which is less than 4. So it's a great idea to use 3 instead of 4 as the second digit because it will give us a smaller number. We will pop 4 out of the solution and we will decrement k. And we continue. We will compare 3 to the new character which is on top of solution, which is 1. It doesn't make sense to use 3 instead of 1 as the first digit, so we will not remove 1. We append 3 and we move to the next character, which is 2. 2 is less than 3, so it's a great idea to use it instead of 3 as the second digit, so we will remove 3 and decrement k. Then we compare 2 to the new character which is on top of solution, which is 1. 2 is greater than 1, so it makes no sense to use it as the first digit. We will keep 1 in solution, we will append 2 and move on to the next character, which is also a 2. Now 2 equals 2, which is an interesting case. If we remove 2 from solution and use this one instead, we will actually get the same solution. So it makes no sense to waste a removal operation, which might help us even better in the future. So we will just append this 2 and move on to the next character, which is 1. 1 is less than 2. So we are going to remove 2 from solution and decrement k. We move on. 1 is less than 2, which is the new last digit. So we would like to also remove this digit from solution, but unfortunately k equals 0 and we cannot do that. At this point we have exhausted all our removal operations, so what we have to do is push all the remaining digits from nums into solution and finish the algorithm. And the solution we obtained is 1219, which is indeed the correct one. At this point, we really understand how the approach will work, but we need to translate it into code. And as you can see, solution is going to be a data structure where we can insert elements to the end of it, and we can also remove elements from the end. So solution is going to be a stack. Even more, you might have noticed that for as long as k is greater than 0, so we have removal operations left, the elements in solution are going to be sorted increasingly. So solution is actually a monotonic stack. When k was greater than 0, our stack was 1, 1, 4, 1, 3, 1, 2, 1, 2, 2, but when it became 0, we cannot make sure that this stack is sorted increasingly anymore, and that is the point where the stack isn't monotonic anymore. Now let's take a look at the code. We will start with a stack which is initially empty. Then we will iterate through all the characters in num. For each current character c, as long as k is greater than 0 and the stack is not empty, and the element on top of the stack is greater than c, then we are going to pop that element out of the stack and decrement k. When the while loop terminates, we are going to append c to our stack. Finally, after going through the whole string num, there is one more thing that we need to do. It is possible that we actually haven't done all the removal operations that the problem asks us to. And if that is the case, and k is greater than 0 after the for loop terminated, then we will remove the last k digits from the stack. So as long as k is greater than 0, we can pop the last digit out of the stack and decrement k. In the end, we should convert the stack into a string, which we will then return. At this point, the time and space complexity of this algorithm shouldn't be unfamiliar to you. We iterate through the characters of num, and each character is only pushed into the stack exactly once and popped out of the stack exactly once. So the time complexity is big O of n. And because we use the stack, which will be of size at most n, the extra space our solution uses is also big O of n.